In this lecture, I'm going to be talking about colligative properties. Colligative properties are properties that depend on the relative amount of a solute present in a mixture, but do not depend on the chemical identity of the solute. And we're going to be looking at three examples of this, three examples of colligative properties. One is the elevation of the boiling point. When you dissolve a solute in a solvent, it increases the boiling point of the solvent. Also, the depression of the freezing point. And the third we'll look at is osmotic pressure. And all of these stem from the reduction of the chemical potential of a liquid solvent as a result of the presence of a solute. And before we proceed any farther, I want to lay down a convention that we're going to be using. We've been more or less using it already, but I want to make it explicit that when we are talking about a solvent and a solute, the solvent is going to be labeled A typically, and the solute is going to be labeled B. Now, if we think back to section 4B, I drew a graph of chemical potential versus temperature. So I'm gonna redraw that graph. So the graph looks something like this. This line is the solid phase, this line is the liquid phase, and this line is the gas phase. And why does it get steeper for liquid and then steeper still for gas? This is because we have this relationship between entropy and chemical potential. And you can see here that I have the derivative of mu with respect to t. That's the slope of this line. And the slope of this line is equal to the negative of the entropy. Entropy is always positive, so we're always going to have a negative slope. And entropy for a solid is less than entropy for a liquid, so that's why solid is less steep than liquid, which is, and that's less than the entropy of a gas, so there's going to be an even steeper negative slope for the gas. Okay, and here at this temperature we have the phase transition between solid and liquid. So this is the freezing temperature. And here we have the phase transition between liquid and gas. So this is the boiling temperature. Also, introducing the notation from the current chapter, where we're talking about mixtures. In the previous chapter, we were talking about pure substances. So this applies for pure substances. So I'm going to put a star on each of these, which is the notation we've been using in chapter 5 for a pure substance. Now, what happens if we add solute to the liquid phase? Well, this is what we derived previously in this chapter. The new chemical potential will be the pure chemical potential plus RT ln XA, which is the mole fraction of A. A in this case is our solvent. And for consistency, I'll go ahead and put A's on these because the liquid is our solvent. So this is the chemical potential of the solvent. And this number right here, ln XA, is always negative. And the reason it's always negative is because XA is the mole fraction. It can never be more than 100%. So XA is always less than 1. And if it can't equal 1 either, because if it does, then we are not talking about a mixture. We're talking about a pure substance, which actually the formula works out. Ln of 1 is 0, so this term goes away, and we're left with the chemical potential is just the chemical potential of the pure substance. Now what I'm going to do is, what happens to the chemical potential of the liquid when I add the solute is that it decreases, because we're adding this negative number to the pure value. So I'm going to redraw this graph, but I'm going to redraw it with the chemical potential of the liquid shifted in the negative direction. Okay, here I've redrawn the graph as I had it before. This is supposed to have a slightly negative slope. I may not have drawn that it looks kind of horizontal, but all of these should have a negative slope. And now what I'm going to do is I'm going to take mu L and I'm going to shift it down. So if I extend this line in both directions, that's the line that I'm going to extend down. You can imagine an infinitely long line that I'm going to extend down, and it's going to end up down here parallel to the first one, but farther down. Okay, so remember that this temperature was the freezing point, and this temperature was the boiling point. When we add a liquid to mu, when we add a solute to the liquid, mu L is here, and we see that it's going to intersect these other lines at different points. So here, this is the new freezing point, and here is the new boiling point. So in this one picture, we see we can make a lot of interesting observations. So right away, we see that when you dissolve a solute in a liquid, the freezing point decreases. And when you dissolve a solute in a liquid, the boiling point increases. Another observation that we can make is you can see that the freezing point shifted more than the boiling point. It decreased more than the boiling point increased. Is that always going to be the case? And the answer is yes, because this line has a shallower slope. So a vertical change is going to cause a bigger horizontal change. This one has a much steeper slope. So a big vertical change is not going to equate to a big horizontal change. So the effect on the freezing temperature is greater than the effect on the boiling temperature. And that's because mu S is much less steep than mu G. All right, and then a quick note I want to make here is that the enthalpy of mixing for an ideal solution is equal to 0. We saw that in the previous section, 5a. So that means delta H is 0. Now, delta H is non-zero when heat is exchanged between the system and the surroundings. So if delta H is 0, then that implies that no heat was exchanged with the surroundings. And so there's no change in entropy due to heat exchange of the system. So the delta S from mixing, the change in entropy as a result of mixing, is what causes the change in the chemical potential. And this is a very similar argument to what we had earlier for perfect gases. All right, so the first example of a colligative property that I listed at the beginning of this lecture was boiling point elevation. So let's take a look at that one. And so boiling point, remember, it implies that at that point we have equilibrium between the vapor and the liquid phases. So in this case, it's the vapor of the solvent and the liquid solvent that's in the solution. And for everything that follows, we're going to let the pressure of the vapor be 1 atmosphere. Okay, so writing this equilibrium down mathematically, it would look like this. The chemical potential of the gas is equal to the chemical potential of the liquid, in both cases for species A, because that's the solvent. Now, the chemical potential of the gas is a pure substance, so it's equal to mu A star. And the chemical potential of the liquid is the one that we saw earlier, which is the chemical potential of the pure liquid plus RT natural log of the mole fraction of A. Now what I'm going to do is I'm going to solve this equation for ln XA. Okay, so first I subtract this over. So I have mu of the gas minus mu of the liquid, and then I need to divide by RT. And if we look at this numerator, remember that mu for a pure substance, these are both pure in the numerator here, mu for a pure substance is equal to the molar Gibbs energy. So this is going to equal the change in the molar Gibbs energy. Because mu for a pure substance is equal to the molar Gibbs energy. All right, now I'm going to take this equation and I'm going to differentiate both sides with respect to temperature. So there's the derivative of the left-hand side and the derivative of the right-hand side. I'll go ahead and pull out the 1 over r because that's a constant. Okay, now I want to focus on this piece right here. We've actually solved this before, or we've written an equation for this piece right here, and that was the Gibbs-Helmholtz equation. So remember the Gibbs-Helmholtz equation, that was from section 3E, tells us that the derivative with respect to temperature of G over T, holding pressure constant, is equal to the negative enthalpy over T squared. And you see we have the derivative with respect to temperature of G over T. This is delta G, so I'm going to use the same argument I've used before. I'm going to do one version of this equation with G initial and H initial, another version with G final and H final, and subtract the two. And just to be sure, is the pressure constant? Yes, remember I said that we were setting the pressure to be 1 atmosphere throughout. Okay, so I'm going to take this result and I'm going to put it in up here. So I get a minus 1 over r, and then this part is replaced with delta H over T squared. All right, so now what I'm going to do is I'm going to separate variables and integrate both sides. So we took the derivative, we used the Gibbs-Helmholtz equation, and now we're going to integrate it back. Okay, so we started with a formula for XA, and we're going to end with a formula for XA. All right, so this is what it looks like if I separate the variables. All I need to do is take this dt and multiply it over here. And now I'm going to integrate both sides of this. Okay, and before we can do this integral, we need to talk about the bounds of the integral. So for XA, let's start XA at 1, which is a pure substance. And we're going to end with XA being any value that I want. I'm just going to call it XA. Okay, so just some desired value. Now we have the ln of XA over here. So when we do the bounds, we need to make sure we're talking about ln of XA, not just XA. So the ln of XA here, if I take the natural log of both sides, I get 0. And then my other bound is going to be XA. And this is the lower bound because it's the smaller number, and this is the upper bound. Okay, so that's for the left-hand side. What about the right-hand side? So when XA is equal to 1, that means we have a pure substance. So the boiling temperature, T, I'm putting a subscript B on here to remind us that it's the boiling temperature. But all of these T's are really referring to the boiling temperature. Boiling temperature is our T variable in this case. So pure substance, we know what the boiling temperature is. It's TB star. Okay, so that's going to be our upper bound for, I'm sorry, our lower bound for T. And then our upper bound is going to be, again, some desired value. All right, so let me put these bounds on the integral. So I have 0 to ln xa over here, and I have TB star to TB over here. And I can put a prime on this xa to differentiate it from the upper bound. Now we're going to do the same trick that we've been doing all semester. We're going to say that since there's a small temperature range, we're dealing with small temperature ranges only, then we're going to assume that delta H is approximately roughly constant. So then I can pull it out of this integral, and I get the integral of 1 over t squared, which is negative 1 over t. All right, so now I'll integrate. So after I integrate, I have ln xa on the left. On the right, this integrated to negative 1 over t, so the negative cancels this negative, and I have 1 over r times the delta h times 1 over t with these bounds. So I'm going to evaluate it at the upper and lower bounds now. And so I have 1 over t minus 1 over t star on the right-hand side. Now, we're talking about a binary mixture here. There's only 2 species present, A and B. Therefore, the mole fraction of B is equal to 1 minus the mole fraction of A. And vice versa. The mole fraction of A is 1 minus the mole fraction of B. So I'm going to make that substitution here on the left-hand side. So on the left-hand side, I end up with ln of 1 minus xb. And I'm going to make a further assumption here. I'm going to suppose that this is a very dilute mixture. So if it's a dilute mixture, what does that mean about xb? Remember, B is the solute. So if it's dilute, there's very little solute. So that means that xb is small. And we've seen, we've done this before. If I expand a natural log into a Taylor series, we see that the natural log of 1 plus x is approximately equal to x for small x. And again, we got that by using the Taylor series of natural log. So if I make that change up here, I get that the ln of 1 minus xb is approximately equal to xb, since xb is small because we have a dilute mixture. I'm sorry, negative xb. This is plus x, so here my x is actually negative xb plus a negative xb. So the left-hand side becomes negative xb for a dilute mixture. All right, so I'm going to take that and I'm going to put it back up here. And I'm going to go ahead and multiply both sides by a minus 1. So that would cancel the negative in front of the xb, and it would flip the order of my subtraction over here. Okay, so this is the equation that we end up with. And I'm going to make another simplification, which is, remember I briefly mentioned that this temperature interval between TB and TB star is small. That's why we were able to pull out delta vaporization H. So since that's true, since TB is approximately equal to TB star, small temperature interval, then delta TB is small because delta TB is the difference between these. And let's see what we can do with that. So I'm going to take what's in parentheses here, and I'm going to find a common denominator. So the common denominator is going to be T star times T, which leaves me with a TB in the numerator over here minus a TB star in the numerator over here. Now I'm going to approximate the denominator by, again, using the fact that TB is close to TB star. So I'm going to replace TB here with TB star in the denominator. I'm not going to do that in the numerator because that would give me 0. And I know I'm dealing with a small number, but I don't want it to be 0. I want it to be a small number. So because if it was 0, we wouldn't get a very interesting result. So a non-zero result would be more relevant. So I end up with TB star squared on the bottom, which is nice because this is a known constant. And in the numerator here, you see that this is the final boiling temperature minus the boiling temperature when it was pure. So this is as a mixture minus when it was pure. So this is the change in boiling temperature over TB star squared. All right, so putting these pieces all together, we end up with XB is equal to the vaporization enthalpy over R T star squared times delta TB. And my last step now is I'm going to solve this for delta TB. So delta TB is going to be 1 over this times XB. So we're going to call this a constant K. This is 1 over this. So K is R T star squared over the vaporization enthalpy. And this is an equation that shows us that the change in the boiling temperature is proportional. This is a constant of proportionality, is proportional to the mole fraction of the solute. So we add more solute, the boiling temperature changes more. All right, and then one more remark about this equation is that notice there's no reference anywhere to the chemical identity of the solute. There's no molar mass. Only the mole fraction of the solute plays a role. And so that shows us that this elevation of the boiling point is a colligative property because it depends on the mole fraction of the solute, but not on the chemical identity of the solute. Okay, so elevation of the boiling point is a colligative property. All right, next I'm going to use Troughton's rule and see what happens if I put that into this equation. So remember that Troughton's rule says that the enthalpy of vaporization over the temperature is roughly a constant. And let me call this constant for purposes here. I'm going to call it CT, Troughton's constant. So let's make this substitution into this equation up here. You see we have delta H over T star. So we're going to end up with a 1 over CT. Okay, so this is actually 1 over CT because this fraction is inverted here. And I have a constant R. So my constant becomes R over CT. And I'm left with one of these T stars. Only one of the T stars was absorbed into the constant, and the other one sticks around. And so we look at this and we see that this number is a constant, the gas constant divided by Troughton's constant. And so from this we can see that the change in the boiling temperature is proportional to the boiling temperature when it's a pure substance. So if a substance has a higher boiling temperature when it's pure, adding a solute to it is going to increase its boiling temperature more than it would for a substance that has a smaller boiling temperature when it's pure. Okay, so that is an interesting result. All right, the next thing I'm going to do is I want to talk about how these things are measured in a lab. And to do that, I need to talk about molality. So I'm going to do a quick aside where I talk about the definition of molality and how we can relate that back to mole fraction. Okay, so the molality, lowercase b is the symbol. And we're talking about the molality of the solute. So that's the species capital B. And this is defined to be the number of moles of the solute divided by the total mass of solvent. Okay, so that's the definition of molality. Okay, so let's say the solution has n moles total. So that's the total number of moles of solute and solvent. In that case, we can write NB as the mole fraction times the total number of moles. And Na, same way, XA times N. And again, since we're talking about a binary mixture, XA is equal to 1 minus XB. All right, now let's say that the solvent has a molar mass Ma. I'll use capital M for the molar mass. So in that case, the total mass of solvent, which was in the denominator of our molality definition, is equal to the molar mass of the solvent, it's mass per moles, times the number of moles of solvent. And earlier, we saw that Na is equal to 1 minus xb times n, so I'm going to make that substitution. So this is Ma times 1 minus xb times n. So now I have everything in the molality formula in terms of xb, the mole fraction. And this was my goal, was to get a relationship between molality and mole fraction for the solute. So now we can write that the molality, which again is NB over little ma, number of moles of B, over mass A. Number of moles of B, I'm going to use this formula because that puts the mole fraction in here. So I'm going to write that as XB times N. And the total mass, A, I found right here, is going to be the molar mass of A times 1 minus XB times N. And you see that the number of moles cancels. And so I've now written the molality in terms of the mole fraction. And this is for the solvent, for the solute. All right, and we've been talking about dilute solutions. Let's see what happens if we have a dilute solution here. Dilute solution implies that the mole fraction of the solute is small, so I'm going to say much less than 1. If that's true, then we're subtracting 1 minus something that's insignificant compared to 1. So this term on the bottom in parentheses becomes 1, and the formula simplifies to xb over ma. And so we see that the molality is proportional to the mole fraction of the solute when the solution is dilute. Okay, so now I want to take this equation, I've labeled it star, and I'm going to solve it for the mole fraction. So I can get, so here I can compute the molality in terms of mole fraction. I'd also like to be able to compute mole fraction in terms of molality. So I'm going to solve it for that. And that's just a matter of taking this denominator and multiplying it over here. So I have that the mole fraction is the molar mass of the solvent times 1 minus xb times the molality. All right, so now I have an XB on both sides, so I need to group this. So what I'm going to do is I'm going to add this XB over here, and to do that it's going to bring along a BB and an MA. So the left-hand side looks like that, and then what's left is this 1 times MA and BB. Over here I can factor out the XB, and then I'll divide the coefficient that appears in front of XB over here to get my formula for XB, which is this. All right, that's the end of my aside on molality. I wanted to get to this formula, which is relating molality to mole fraction, because mole fraction appears in our elevation of the boiling point formula that we had before. Remember, where delta T, the change in the boiling temperature, is equal to a constant times XB. So here's our mole fraction. And so this equals, remember this is the value of K, R T star squared over the enthalpy of vaporization. Okay, and as we just saw in the aside, for a dilute solution, we have that the molality is proportional to the mole fraction. If I solve this for XB, now I can plug this in for XB up here. And I get that the change in the boiling point is this times MA BB. And this is a constant. And we're going to call this constant the boiling point constant, KB. So with that label for the constant, the formula looks pretty simple. That the change in the boiling point is proportional to the molality of the solute. And this is something that can be measured in a lab very easily. So that means we can measure KB easily. And so what we have then is we measure these, we tabulate them for different substances, and we have a table, you have one in your textbook, that has all of these boiling point constants for various substances. One last thing I want to point out about boiling point is I made the claim that it was colligative, and here we see that we've introduced a dependence on the chemical identity of something, right? The molar mass is going to depend on what the chemical formula is. However, this is the chemical identity of the solvent. We still have not introduced anywhere anything that has anything to do with the chemical identity of the solute. So we're still okay. This is still a colligative property, even though we have introduced MA. We're only talking about the chemical identity of the solvent. Okay, so let's talk about the second item on the list of colligative properties, and that was the depression of the freezing point. So it's going to proceed very similarly to before, and so this part will be pretty short because we've already done most of the work. So remember, at the freezing point, the solid and liquid phases are in equilibrium, so their chemical potentials are equal to each other. And over here, we're talking about a pure solid, whereas over here, we're talking about a liquid that's in a solution. Okay, so that means the left-hand side is just going to be mu star of the solid phase. And the right-hand side is going to be the formula we've been using for ideal solutions throughout the chapter. And this is a very similar beginning to what we had before. The only difference is that instead of a gas on the left-hand side, we have a solid on the left-hand side. So all of the analysis is exactly the same. And what we end up with is, so the change in, this time it's the freezing point, is proportional to the molar fraction of the solute, where the constant of proportionality K prime looks a lot like the one we saw before, except it's the freezing point of the pure substance squared, and on the bottom it's not the enthalpy of vaporization, but the enthalpy of fusion. And also, as before, if we have a dilute solution, then we can write this as the change in the freezing point is equal to this constant times the molality, where this constant now we're calling the freezing point constant. And this is another quantity that can be measured in the lab and tabulated. And you'll find a table of those values in your book. Okay, and I'm going to stop here for this video. We made it to page 100 in my notes, so it's a landmark. Next time I will talk about the third colligative property that I mentioned, which is osmotic pressure. All right, see you in the next video.